Hello, my name is Bing. I'm writing senior major in electrical engineering at the University of Michigan. This summer, I was involved in a project about gyroscope. Gyroscope, by definition, is a device to measure the orientation, or we can say the angular velocity. This figure shows a traditional mechanical gyroscope, and we can see from the animation that the rotor maintains spin axis direction regardless of the orientation of the outer frame. In this way, we can get the change of orientation. This kind of gyroscope is still used in airplanes. However, because of its mechanical structure, the size is too big. If we want to make a gyroscope in a hand-on device like a mobile phone, we need something looks like this, and that is the MEMS gyroscope, or called the micro gyroscope. From its theory, I prefer to call it the Coriolis vibration gyroscope because the true physics theory behind is 1. Vibrating object tends to vibrating in the same plane, and 2. The response detected by the transducer results from the Coriolis force. This animation demonstrates the Coriolis force. The observer standing on red dots sees the object as following a curved path due to the Coriolis force and the centrifugal force. This is the very typical one-axis single-mass microgyroscope. There are two drive electrodes along x-axis and the sense electrode along y-axis. We apply a sinusoidal signal on drive electrode so that the mass would vibrate along x-axis. During the rotation, the Coriolis force will make the mass vibrate along y-axis. This vibration changes the capacitance of sense electrode. By measuring the change of the capacitance, we can get the Coriolis force and the speed of rotation, which is the orientation. The MEMS gyroscope is widely used in many areas: the automotive, like airbag, spacecraft, entertainment, like mobile phone, tablet, and game console, and the photograph, like image stabilization system. This picture shows the gyroscope in iPhone 4. Besides drive electrode, it has 3 pairs of sense electrode to detect angular velocity along 3 axes. Let's see its work results. So this is the evaluation board for the gyroscope in iPhone 4, and we can see this is the real MEMS gyroscope. It has the digital signal output, and through this board into my computer, we can see that the bar graph represents my angular velocity in around 3 axes, and it is very sensitive. This gyroscope is a gyroscope in our research. It is called the balanced oscillating gyroscope. It vibrates in x-y plane. During rotation, the Coriolis force makes the mass have a displacement in z-axis, so that the capacitance between mass and the sense electrode beneath it will change. In the testing, we apply drive signal with different frequency and want to find the quality factor and the resonance frequency. The quality factor is how underdamped an oscillator is, and the resonance frequency is the frequency the mass should vibrate. So this is the equipment we use to testing the gyroscope. This is the gain phase analyzer, and we can see this is the plot of gain phase, which can be used to capitalize the characteristic of gyroscope. There is a signal output from here, and this is the vacuum station. The gyroscope is put into this chamber. There is the signal output goes through this cable and reach that board, which converts the change of the capacitance to the voltage, and go back to the gain phase analyzer so that we make the comparison between the input signal and the output signal. This is one of the results we get from testing. From the gain phase analyzer, we can find the true peak, and there are drive mode and sense mode. From the graph, we can measure its resonance frequency and quality factor. And this table is the summary of testing and its statistics. Its quality factor is around 5,000, which is the good result. In the future, we can make other testing, like put gyroscope on rotation table and test its sensitivity. This project was sponsored in part by a grant from Defense Advanced Research Project Agency. Thank you.